were talking about ceramics on Thursday, and I was showing you some of the crystal structures of ceramics. Okay, this is the rock salt, NaCl. This is one individual unit cell with the cation as in the FCC structure, and then you can see where the anion is overlaying the cation unit cell. And if you were to look at the material in a more realistic view, it would look more like this, where you can see that the cation has a FCC structure, and so does the anion have a FCC structure. And when we look at the coordination number, we can see that each cation is surrounded by 6, 1, 2, 3, 4, 5, and the one in front, 6 anions. And every anion is also surrounded by 6 cations. So it's a 1-to-1 ratio, which makes sense because this is NaCl. The next one I wanted to show you is the cesium chloride. So we talked on Thursday that this is a simple cubic. So my chlorine is in a simple cubic structure, and so is my cesium. So you can see the cesium structure here, simple cubic. What is the coordination number here? How many anions surround my cation? 8. And how many cations surround my anion? Also 8. Right, so again, that makes sense because we have a 1-to-1 cesium to chlorine ratio. So that's a cesium chloride. Then we have something called the zinc blend. The zinc blend is 2 FCCs. Can you kind of tell how much is shifted by? So this is 3/4 of the way, 1/4, 1/4. Okay, so this is called the zinc blend. This is an individual unit cell. I know it's not easy to see, but the overall structure. This diagram here makes it a little bit easier for you to see the coordination number because it actually shows you the connection where this atom, which atoms this one is touching. So this is touching 1, 2, 3, 4. So the coordination number for zinc blend is 4. And again, it's a 1-to-1 ratio. Okay, but what happens if you have a ceramic material that's not 1-to-1 between cation and anion? Well, it could take on something that looks like this. This is called a fluorite. So if you look at this individual unit cell, the green one, that's an anion probably because it's bigger. So the anion, how many atoms do you have in the unit cell? How many total atoms? 4, right? You have 8 corner ones, but each one is shared by 8 other unit cells. You have 6 face center ones, and each one is shared by 2. So the total number is 4. So you have 4 anions. And how many cations do you have? All of them are actually embedded completely within the unit cell. So you just have to count 8, right? So you have 8 cations. So you can have a structure like this when you have, so if this is Y, X, so it has a formula of 2 anions. Okay? So if you have a not 1-to-1 ratio between the cation and the anion. And then it could get really, really complicated. I don't know if I put one on here. So you can have, some ceramics have 3 elements, right? So it can get into quite complicated structures. And you're not going to need to memorize anything like that. If you eventually end up working with ceramics in industry, those are all things that you could look up in a handbook or online. And so the main idea here is to understand that ceramic materials are also crystalline. They have crystal structures, and that these crystal structures have to balance between the cation and the anion. That the size difference between the cation and anion is important, especially if it's ionically bonded, right? And that the structures can become very, very complicated. So one of the really, really important ceramic materials is glass, or silica, SiO2. And this is one of the most important ceramics that we work with. And any thoughts about whether this is a mostly ionic or mostly covalent material, ceramic? So silica is in row 4. Oxygen is in row 6 on the periodic table. It's mostly covalent, right, because they're very close to each other on the periodic table, very similar electronegativities. And SiO2 forms a tetrahedral. Sorry, I did have a structure with multiple, so going back to a complicated ceramic materials, this is something that may have 3 different elements, another one, and this is something called the perovskite. So again, just another, for your reference, something that can look like that. All right, so silica. Silica forms a tetrahedral. A tetrahedral kind of looks like a pyramid. Is with Si in the middle, connected to 4 oxygens. So the pyramid kind of looks like this, with Si sitting in the middle of that pyramid. In the corners of the pyramid is oxygen. So the silica shares 4 electrons. It's in row 4, so it has 4 electrons to share. It shares 1 with each oxygen. Oxygen is in row 6. It wants to have 2 more electrons, so it needs to be bonded to another silica, right? Okay, so they are actually connected in this way. So the oxygen on this tip is connected to another silica in a different tetrahedral. So this shape is called a tetrahedron. Okay, so the Si and O form a tetrahedron with the Si in the middle, and the oxygen on each tip is connected to the center of another tetrahedron where you have another Si. So all of the oxygens are connected to 2 silica, and all of the silica are connected to 4 oxygen. That's the basic structure of any kind of silica. Silica is SiO2. This is what so here you see, this is the silica, these are the oxygens. It's just a 2-dimensional, it doesn't show all 4. But you can see that on this side, you have kind of a random connection, right? Every oxygen is connected to 2 silica. Every silica is connected to 4. It's on the 2-dimensional plane, you only see 3, but it's connected to 4 oxygen. But on this side, it's kind of a random connection. On that side, you have something that is organized or ordered. So I'll talk about the disorganized one first. So that's glass is an amorphous solid. Amorphous means no long-range order. There is order in glass because every silica forms a tetrahedron. But in terms of long-range order, if you look at it over 100 molecules, it's going to look random. And so anything that doesn't have a long-range order, it's called amorphous. So glass is the most famous amorphous solid. There are many other amorphous solids, including some metals. Some metals, depending on how you manufacture, you can actually make them amorphous. Much more difficult than glass, but you can also do that. So glass is one of the oldest man-made, well, not man-made necessarily, exists in nature, but humans have figured out how to manipulate glass for a long, long time. Okay, so it was probably discovered by some people camping on the beach. Okay, right? They set up a fire to cook their food and things, and then the next morning when the heat died down and they were leaving, they noticed some glass underneath their fire. Okay, that's probably what happened, how glass was first discovered. Because silica, sand, is made up of mostly SiO2. And so glass that probably happened that way. But if you look at just pure silica glass, so SiO2 has a melting temperature of around 1700 and something called the glass transition temperature of 1000. So very, very high temperatures. Glass transition temperature, because glass is amorphous, it actually goes through a transition where it is still mostly a solid, but you can work with it, you can manipulate it, it becomes soft. So I don't know if you've seen shows about glass blowing at the Hsinchu Glass Museum. They have a little workshop. They're always making something, so if you've never seen anyone blow glass, you could go there. It's very close. You can see them blow glass. And they put it in a furnace to heat up a little blob of glass that they have. And then when they take it out, it's glowing red usually, and then they could, shape it, blow on it, make a ball, something, right? And then when it cools down too much, they need to soften it again. They put it inside the furnace again. So what that furnace is doing is putting that piece of glass above the glass transition temperature so that it's workable. So that's what glass transition temperature means, is the temperature where the material becomes workable. So it doesn't melt, doesn't become a liquid completely, but it does become workable, okay? So glass transition temperature is very important when you're dealing with glasses. So it is unlikely that the first people who made or discovered glass made pure silica glass because the temperature is so high. It's unlikely that their campfire could reach 1,700 degrees Celsius. So it is most likely that the sand that they were staying at had some impurities. And it's very common to have calcium oxide, and sodium, which mixed in to the glass to form what is called the soda-lime glass. A soda-lime glass will have a glass transition temperature of about 550 degrees Celsius. Okay, so much, much lower. Pure silica glass is very, very transparent. And it actually is transparent into some UV and also some infrared. And so it does have a lot of really good technological uses for pure silica glass. It is also very hard, but it is harder to work with because of its high glass transition temperature and high melting temperature. And so most of the time, the glasses that we use today, like for windows and for your glass bottles, things like that, things that you use around the house, those are all going to be most likely soda-lime glass. And soda is Na2CO3, and calcium oxide is called lime. So soda-lime glass is just silica with Na2CO3 and CaO added into it. It lowers the working temperature, but it also makes this glass less chemically stable. So a lot of times people also add alumina and magnesium oxide, and this increases its chemical stability. So soda-lime glass is found in a lot of things. Something that soda-lime glass doesn't do that well is high temperature performance. So soda-lime glass tends to expand quite a bit when you heat it. So that means if you were to heat it quickly, it will try to expand, but because glass is a ceramic material, it's brittle, it doesn't allow for changes in its shape very easily, it will crack. And so it doesn't work that well if you want to heat it quickly, cool it, put it in the oven. It's not a good glass for that. So for cookware, usually people use borosilicate glass. And that's what Pyrex is. So it's with the addition of boron oxide and a lot of labware. So if you're doing experiments in the lab in your chemistry or other material science classes, most of your labware, beakers, things like that will be made out of Pyrex, which is borosilicate, and also cookware. So if you have glass that is, as a dish for baking or cooking, most likely will be a borosilicate. because it has very low thermal expansion. So Corning is a glass manufacturing company. I mean, they do a lot of other things, but they're very well known for manufacturing glass. And they developed the first really heat-resistant glass ceramic material. And some of their materials, it's quite smart, the way they worked on it, is that they have materials, molecules, because when you heat something, the bonds expand, right? It's really difficult to prevent something from expansion because you're adding energy with heat, the molecules are vibrating, and so the bond length is going to elongate. But what Corning developed, this is not necessarily borosilicate glass, but what Corning developed is a material where the bonds will elongate, but only in one direction. So it will elongate in one direction and shrink in the second direction. And so if you have lots of materials inside, and some of them expand, but shrink in this direction, and others expand in this direction, but shrink, then the expansion and the shrinkage will even out, will average out to be no difference in volume, right? And so Corning developed one of the first things, ceramic materials like this. It's Corning cookware, and it's very popular and still used. There are, I don't want to say the wrong thing, because these are companies that make a lot of money. I think what happened was that Corning sold their technology. So if you were to buy certain kinds of glass or ceramic that says that it's Pyrex, or I should really look this up before I tell you, but there's a brand. So let me not say Corning or Pyrex. There's a brand that was very, very well known for a long time as a heat-resistant glassware ceramic material. And recently, if you were to buy it within the last 10, 15 years, it will have very poor performance because the company that sold it, the name to somebody else, the new company doesn't make it the same way. So even though it has the same name, it has different performance. And so sometimes if you want to buy heat-resistant cookware, it's important for you to make sure that it is a high quality. So just having the name doesn't necessarily mean that it's going to be a high quality material anymore, unfortunately. And then another common glass is called aluminal silicate. It has the addition of alumina, Al2O3. It's very difficult to work with. It has a very high glass transition temperature, but it has even lower thermal expansion than borosilicates. So it's actually used in things like higher tech materials and also fiberglass. Almost all fiberglass materials are made out of aluminal silicate. So these are the kinds of amorphous silica. So amorphous silica or glass has these different applications and uses and properties. And if you were to look at crystalline silica, it's called quartz. It has very high reflectivities, can look very shiny. So it actually is gemstones. A lot of gemstones are made out of quartz. So this is a quartz that's not colored. The other colors come from different kinds of inclusions or impurities. So if you have different kinds of impurities inside, you'll also see they'll manifest itself in the different colors of the quartz. Glass, amorphous glass, can also be colored by different kinds of inclusions. And the most common one is small amounts of iron. So if you look at like car glass, window glass, a lot of times you'll see like a slight green tint to it, and that comes from the trace amounts of iron in the glass. Something kind of interesting I thought was the way they make really large, flat pieces of glass, going back to glass. Anyone have ever seen glass manufacturing, especially large flat sheets? How do they make it so flat? So there's a myth out there that says that glass, because it's amorphous, it's really a liquid and not a solid. Has any of you ever heard that? Okay, and then they actually say that it's just a liquid that flows very, very slowly, and that if you were to look at very ancient glass, at like in European cathedrals or something, the old glass is actually thicker on the bottom and thinner on top because the glass has flowed over time. So that's not true. They've never proven that. The glasses that they used to make in those European castles are just uneven in general. They're not completely flat. They have thicker and thinner parts to them because of the glass making technology back then was difficult to make a completely flat piece of glass. Glass is a solid, it's not a liquid, it doesn't flow, at least not in our lifetime or the lifetime of any material that will be used. There has been no evidence of any kind of flow at working temperatures. Of course, if you take it to the glass transition temperature, it will flow, but not at room temperatures. So the way they make glass, and you don't want to make a piece of glass, so like if I were to pour glass onto a piece of metal and let it cool down, right? It's going to take on any of the imperfections of that metal. And so that surface will not be perfectly smooth. It's really difficult to have something that's perfectly smooth. And you don't want to have to spend time and energy to polish all of that, all of these windows. If you had to polish all of them and sand it down to be perfectly flat, it would be very, very expensive. So you don't want to do that. So you want to be able to float the glass because liquids are perfectly smooth. The surface of a liquid is much smoother than the surface of any solid. Solids get scratched, indented, but liquids, if it gets indented, it'll just flow back to a solid, right? To a smooth surface. And so they actually float the molten glass on top of mercury or lead. So some sort of liquid metal that's very heavy, and then they could float the glass on top because glass is much less dense, and they could just let it cool that way. So as long as the metal that is floating on has a lower melting temperature than glass, so the metal will stay liquid as the glass solidifies. Then they can make huge, huge pieces of glass that are perfectly smooth, and that's how they do it now. Okay, back to quartz. So it's crystalline SiO2, it's very pretty, but it also has a very, very important technological application, and that's because it's a piezoelectric. Anyone heard of that word, piezoelectric? Piezoelectric material is a material that can produce a voltage under mechanical stress and vice versa. What that means is you take a piece of quartz, you squeeze it, and it will produce a current or a voltage. And you let it go, and that voltage will go away. You squeeze it again, it'll produce voltage. You let it go, the voltage will go away. And it works the other way around. If you supply a voltage to the material, it'll change its shape. You remove the voltage, it'll go back to its original shape. So the shape of the material is related to the voltage that you apply or it's being produced. So it's used as an oscillator. It can be a very, very accurate oscillator. So you apply a current to it, you alternate that current, and the material will vibrate according to the frequency of your voltage application. And because it is easy to control the voltage, then it's easy to control the vibrational frequency. It's very, very accurate. So it's used in a lot of timepieces, like watches. So in a watch, when you have a battery, what is that battery powering that's keeping time? It's a quartz piezoelectric. That battery is applying a voltage to the piezoelectric, that quartz. The quartz is vibrating. The watch is calculated to or calibrated to how many vibrations per second. So whatever the number of vibrations, it'll tick the second hand 1 second. Okay, so you could buy, so most watches, most inexpensive watches will have a quartz movement on the inside because it's very, very simple. Doesn't have a lot of moving parts to this quartz. You just have to have a battery, right? When the battery is dying slowly, then the watch may start to slow down, and then you need to change the battery, and then it'll start working accurately again. The really expensive watches that you can buy actually are less accurate because they actually use a spring. The reason why it's more expensive is because spring-driven watches are harder to make and involves more mechanical pieces in order for it to work. And so so people are paying for the craftsmanship, how difficult it is to make, how many pieces are in there, but you're actually buying a timekeeping instrument that's less accurate by spending so much money. So a quartz is still the best, most accurate. I don't want to say the best. It depends on what you want. If you want something beautiful, then maybe you don't care about how accurate it is. So quartz is used in a lot of things that require very accurate timekeeping as a piezoelectric material. So any questions about ceramic materials? Anything that you've always wondered about ceramics that maybe you've never asked about or don't know? Any of you taken like a ceramic making class? Make clay and then you put it in the furnace and you bake it. Any of you done that? And so most of what you're going to be using in that ceramic class is a lot of aluminum silicates. They're given different names. I don't know all the names in Chinese, but it'll have content. Its content will have a lot of silica, SiO2, definitely have alumina in it, but probably some magnesium, calcium, carbonate, other things, depending on the color that you want to end up with and how hard you want the material to be, and also at what temperature you're going to heat it, right? It depends on what you want that clay material to be. And a lot of times what you will do is add a binder because you start with a powder and you add water to it, but it doesn't hold very well. So you usually add a binder, something, probably some sort of polymer, and that polymer will burn away. So when you first put that ceramic material in the furnace, it's before you heat it, it's called a green body. I'm not sure why it's called green body. It's not green, but it's called the green body, and you put it in the furnace, and the little pieces of particles will start to grow together through diffusion, so they'll connect. So instead of, when you take your ceramic out of the furnace, it's actually not individual particles packed together anymore. It's actually connected, covalent or ionic bonding, depending on what you're using. And it will be very, very strong because of that bonding. But it does take time and high temperatures for diffusion to occur and for that growth to occur. The binder will burn away, and that's one of the problems with making ceramic materials for high-tech applications is that a lot of times you need binder to hold it, but when the binder burns away, you're losing some of the volume. And so it's actually quite difficult to make high-tech ceramics that have a very specific, accurate dimensions, the size, because you're actually going to be reducing the volume as you burn away the binder. So actually it does take a lot of work to use as little binder as possible, but also in terms of how slowly you burn away the binder, how you let the crystals grow, and so forth. So there's a lot of work that goes into a ceramic material. Ceramic materials are really good, very, very hard, right? They are high stiffness, they won't bend. And if you can prevent it from cracking, it's very, very strong. But because of the way it's made, it needs to go under high temperatures. And that limits what else you can add into the glass or the ceramic material. And so when I was doing my PhD, I worked on ceramic materials that are made through the sol gel process. So it's actually a liquid way to make ceramics. A lot of, so ceramics are metal, usually connected to some kind of non-metal, oxygen, nitrogen, carbon, so on and so forth. But a lot of times you take a metal connected to organic group, and this is a liquid. And then you could swap out the R through a chemical process. It's called hydrolysis and condensation, but basically you could use a liquid to do a chemical reaction where you make something like this, a metal connected to oxygen or carbon. And this could be done in a liquid process. And you end up forming, so this is your liquid, you pour the precursors in, you add a catalyst, you end up with this, but you're still in a liquid state, so you have MOO like this, something like that. You have this amorphous structure within the liquid. So, and the trick then is to get rid of any of the liquid and maintain the shape of the solid. So metal to oxygen bonds form a solid. It's very, very fragile, and it's filled with liquid inside the pores. But if you can remove the liquid without disrupting the structure of the solid, then you get very high surface area, very porous, and amorphous ceramic material. So it's a ceramic material that is very unlike any other ceramic materials. You can make magnesium oxide, you can make vanadium oxide, titanium oxide, and they will be transparent. And they will have very, very high surface area. Some as high as 1,000 meters squared of surface area per gram of material. Okay, so it's very unusual, and because you're making this through a liquid process at low temperatures, you can actually add different things in there. You can add polymers in there. Usually you can't add a polymer into a ceramic material because just like the binder will burn away when you make your ceramic, right? You can't add biomolecules into a ceramic because they'll burn away when you make the ceramic. But through the sol gel process, you can add lots of other things that normally you wouldn't be able to add because you don't have to take the material to such high temperatures. And so you can make a polymer ceramic material that has very high thermal resistance. It can go up to very high temperatures but still be flexible. And you can embed biomolecules into these ceramic materials and use it as sensors. So you can have a glass silica with biomolecules embedded within that can either change color or give you some sort of signal when it's detecting something. Okay, so NASA uses silica so these are called aerogels. When you make them this way, it's called an aerogel. So NASA uses aerogels as thermal insulators because it has such high porosity, it does not conduct heat very well. So it's very, very light and can be used as thermal insulators. So that's a different kind of ceramic material. You can make them from a lot of different kinds of elements, but if you do it through the sol gel process and you get a very high surface area, then they're all called aerogels. So I want to talk about polymers next. So polymer is anything that is made out of a long chain of individual units. So a chain of subunits. So DNA, it's considered a polymer. The naturally occurring polymers, like rubber from rubber trees, right? Rubber is made from a sap from a tree. So that's a naturally occurring polymer. A synthetic polymer, usually we call them plastics. So plastic, it's a man-made or synthetic polymer. And we were talking just now about how glass is one of the oldest materials that people have learned to make. Plastic is one of the newest materials that people have learned how to make. It was actually first created in the late 1800s, and they were made from cellulose. Cellulose is like a fibrous material from plants and is used to make paper. But if you can use a chemical reaction to cause the units to join, you can actually get a plastic material called celluloid. And celluloid was a lot of old film was made from celluloid. Film as in like to take pictures and photographs and movies, that kind of plastic. And the subunits was C6H10O5. So you get these subunits and you are connecting them together. That would be a celluloid. And it wasn't really in the late 1800s, nothing much really happened with celluloid. It was a new material, but it wasn't until early 1900s, in 1909, someone developed bakelite, which is also a plastic material. And here's a picture of different kinds of materials made from bakelite. So bakelite, many different colors that you can make. It's a very stiff, hard material, but it's very easily molded because plastics do not need high temperatures. So as long as you can make a mold, you can cast or extrude the plastic in almost any shape that you want. Fairly cheap. Again, because you're not taking it to high temperature, you could put the dye, the coloring, into the material, and that color will be throughout the material, right? If you have a wood, so think about any of these things. What would they be made out of if you didn't have plastic? The phone, the jewelry, pool balls. Anyone know what pool balls used to be made out of before they had plastics? What is it? Metal? No, not metal. Wood is too light, right? So if you think about the pool balls the way today, like it's heavy, it's very smooth. It can't, when you hit it against each other, it can't break or crack. Okay, so it's not a ceramic material. They didn't make it out of ceramics. It's not wood because that would be too light. It wouldn't have the same feel. Pool existed before they had plastics. So when they made plastic pool balls, they were trying to replicate what the original pool balls felt like, the weight and the way it sounds when it hit each other. Can you think of something that would behave that way? So they actually made them out of ivory. There are also some for cheaper ones made out of stone, but most of them were made out of ivory. Okay, you can kind of see how ivory would be a similar way. I don't know if any of you play mahjong. Mahjong tiles also used to be made out of ivory. I don't know if you knew that, but now they're mostly made out of plastic, right? So if you can imagine that you needed that much ivory for every pool game, that is a very expensive game, very expensive to play pool, and that's the way it was. Pool used to be a gentleman's game, and only very rich people played pool because other people wouldn't have access to pool balls. Piano is another one. Piano keys used to all be made out of ivory, and now they're made out of plastic, of course. So a lot of things that used to be expensive and difficult to obtain, when you got plastics, it made it accessible to a broader public. It became much, much easier to make and to do those things. So piano started to become more common for people to play because pianos are still very expensive, but at least you don't need ivory for the keys. And then certainly pool became a very common, popular game amongst just anyone, okay, because now you don't need ivory. And you can make telephones of different shapes and colors. If you were to make those telephones out of, say, metal or wood, you probably wouldn't do ceramic. Let's say you made them out of metal or wood, it would be difficult to color, right? You could paint the surface, but the paint would rub off or chip off. But when you use plastics, the dye, the coloring, is embedded in the plastic. It's the same color throughout. And so it doesn't matter if it gets chipped, the color still remains the same. And so bakelite, or this plastic that was first made in 1909, became very, very, very popular. And it was used in jewelry, in everyday housewares and games, and pretty much anything that you can make plastics out of, that they made it out of bakelite. Toothbrushes, combs, anything. And it was now easy to make these things mass-produced because lower temperature of production, you can just take the plastic liquid and cast it into a mold or extrude it into a shape and cool it down, and you could do this very, very quickly. So that was in 1909. And then during the wars, both during World War I and also but especially in World War II, the development of plastic became important for the military. And it was actually a lot of plastic. So during that time, during wars, many countries put a lot of money into the development and discovery of new plastic materials. A couple of reasons. One, tires of tanks and airplanes and trucks are used to be mostly made out of rubber, right? Rubber came from rubber trees, which is really only grown in certain areas of the world. A lot of it's from Southeast Asia. So the sap, you have a rubber tree and you collect the sap, the liquid part of the tree, you collect that and then you could treat it and it becomes rubber. But in a war, your supply chain can get interrupted, right? You have more difficulty bringing the rubber from far away. And so the countries wanted to have some independence from this kind of supply chain interruption. And so spent a lot of money to develop synthetic rubbers. So what can we use instead of natural rubber? Can we make our own? So we're not dependent, our military infrastructure is not dependent on supplies from other parts of the world. And one of the first synthetic polymers that was made after Bakelite was polyethylene. So polyethylene has a unit C2H4. I'll write it this way. Because we said a polymer is a long chain of subunits. So a polyethylene and this would be one subunit, C2H4. So this is a subunit of polyethylene, C2H4. This chain can be thousands, tens of thousands of molecules long. And so if you imagine this extending for thousands or tens of thousands of molecules, it makes a very long chain, and chains that are that long tend to get bent and tangled, right? So the polymer chains will probably look something like this. Another chain, something like that, okay? Kind of like a plate of spaghetti or noodles. Polyethylene was first developed as a radar shielding material. And it was highly guarded as a national secret how to make this because it was used in war. But then once it became public knowledge, it's used in almost everything. So your plastic bags are made of polyethylene. Your bottles, water bottles, plastic water bottles are made of polyethylene. Biomedical applications like hip joints, artificial hip joints and knee joints, those are usually made of polyethylene. Pipes, water pipes are made of polyethylene. Okay, so lots and lots and lots of, probably the most common polymer plastic that we use in our everyday life is polyethylene. And there are different kinds of polyethylene. But before I go into that, let's talk about why polymers are so elastic, or why is it so easy to stretch a plastic material. A plastic material like this, you could stretch it because the chains are not bonded to one another, right? Maybe they have some secondary bonding, hydrogen bonding between the hydrogens, something like that. But there's no covalent or ionic bonding between the chains. And so when you stretch it, the chains just slide past each other. And they could elongate, right? There's nothing stopping them from stretching. And so that's why plastic materials can be so stretchy, very elastic, have high amount of strain. You can control that. If you don't want your plastic to be so stretchy, what might you be able to do prevent it from just sliding past each other, you think? What would you want to do? Right, you lock the chains together, right? You don't allow them to slide past each other, and that's called cross-linking. You form primary bonds, so either covalent or ionic bonds between the chains. So you could put in a bond here, something like that. You put in primary bonds, and now it's much more difficult for the chains to slide past one another. So the degree of cross-linking, how much cross-linking you put in, will change the elasticity of your plastic. So you can make polyethylene a couple of different ways. So there are lots of things that you can control in plastics. One, you could control the chain length. You could control whether you want a long chain or a short chain, depending on how you make the plastic. You could control the amount of cross-linking that you have, right? And so there are lots of different kinds of polyethylene. Some of the ones that you probably heard of, I don't know if you've ever seen this, HDPE, high-density polyethylene. Okay, high-density polyethylene. It's a lot of times in a recycling symbol. It'll say HDPE, so people know how to recycle a high-density polyethylene versus a low-density polyethylene. High-density polyethylene is formed slowly. So polyethylene, like a lot of plastics, are extruded into its shape. So you just push the liquid material through a hole and form a shape, like a fiber or something. And high-density polyethylene is extruded slowly. So it's pushed through that hole slowly. The rate of extrusion allows the chains to line up. And so you end up with chains like this in a high-density polyethylene. And because the chains line up, you can pack more of the chains together. So it makes it high density. And oftentimes you can cross-link it because the chains are so close to each other. You get lots of places to cross-link. And so it becomes very strong. So high-density polyethylene usually is not that flexible, but it has much higher strength than low-density polyethylene. And usually it's not transparent. It's usually white because it has long range order. It's almost like a crystalline material because things line up. So it's usually white in appearance because it scatters color. Of course, you could dye it and make it different colors. Okay. So this is high-density polyethylene. You can have low-density polyethylene. This is extruded quickly, and you don't allow time for the chains to line up, so you get a more jumbled material. So it has lower density, it's not as tightly packed together. And if you don't add any cross-linking, it's also very, very stretchy. So a lot of plastic bags are made from low-density polyethylene. And actually, I think I saw a question in that survey I gave you in the very beginning of class. Somebody asked why plastic bags become white when you stretch it. I don't know if you ever wondered about that. So you take a plastic bag that's transparent or mostly transparent and you stretch it. You're going to notice two different things. As you stretch it, when you first start to stretch it, it's really easy to stretch. As you get closer and closer to its breaking point, it becomes harder and harder to stretch, right? It becomes more stiff. And it also can start to get striations of color, like it turns white in strips, right? You notice that, okay? Knowing what we know now about plastics, any thoughts about why those two things happen? So let's talk about the first one. Why do you think it gets harder to stretch as you stretch the plastic bag? Yeah.
Because we start to break the primary bonds.
Right. You start with this, right? When you first stretch it, you're only breaking secondary bonds. You're allowing the chains to slide past one another. So you start to get maybe like that. The chains slide past one another. You continue to pull that. You're going to get the chains all to slide past one another and stretch out almost completely fully, right? You continue to stretch, and it's going to line up because you're pulling on the chains. So the chains tend to stretch out. At the very end, if you want to keep stretching, you're going to have to break some of these bonds. And those are primary bonds and not secondary bonds. And so it becomes much more difficult to stretch and break. So eventually, if you want to completely break the plastic bag, then you're actually breaking all or mostly covalent bonds because it's carbon to carbon. It's a very strong covalent bond, right? Just like in graphite and diamond, carbon to carbon bonds are very strong. So at the very end, you're actually breaking mostly just covalent bonds. So that's why it becomes much more stiff as you stretch it. Why do you think the color changes? Why do you get these strips of white that appear? So you're getting regions that are mostly crystalline, right? So the part that you see the white, you're forming not exactly high density polyethylene, but you're getting areas where everything's lined up and it's crystalline. And why would crystalline things be non-transparent versus transparent materials? We actually talk about that on Thursday next week under electronic properties of materials. Optical properties, actually a subsection of electronic properties or electrical properties. And so we'll touch on that. But crystalline materials tend not to be transparent. And it's not always true, but most of the time, crystalline materials are not transparent. Amorphous materials are. And so you'll see as you form these crystalline areas of the polymer, they become white. And the parts that are still amorphous is still transparent. So the chains can be long or short, so they can have different lengths. When you talk to a polymer scientist, they'll refer to this as molecular weight of the polymer. So a polymer with high molecular weight means it has longer chains, and low molecular weight has shorter chains. Polymers can be crystalline or amorphous. I know we usually think of plastic materials as amorphous, but that's not always true. They can be crystalline. And they could be branched or linear, the chains. So this would be a linear chain. So even though they're curled over on top of each other, it's still just one singular chain. But you can get chains that have branches. And this is by adding something here. So you could add maybe oxygen that connects to another carbon, to nitrogen, something like that, right? So you could swap out one of the hydrogens on a polymer chain with something else and cause it to have branched structure. A branched polymer would be more likely to be cross-linked because you have more areas for cross-linking and more areas for the chains to get tangled up. So it's common for branched polymers to be stronger. Another really common polymer that you probably have heard of is nylon. Nylon it's made from petroleum byproducts. Nylon is a carbon chain with mostly hydrogen, but some side groups. So these are what are called side groups. So depending on what you add as a side group, what kind of compounds you add, and also how many side groups you add, it will change the behavior of the plastic. And so that's another reason why plastics is so useful. It's because we have such high level of control over the behavior of plastics. If you think about metals, we make metals, lots and lots of metals, but they're really, really difficult to get them to change their properties, right? We could make them a little bit stronger, a little bit harder, more corrosion resistant, but if you look at a piece of metal, this still all looks and behaves as you expect a metal would behave, right? It's kind of shiny, has high thermal conductivity, it's pretty strong. It can bend, it's pretty tough, but it's not super soft. You look at ceramics, same thing. Most of the ceramics we see really hard, brittle. Yes, you could change the formation temperature, you could change the density, the reflectivity, but it's going to look like a ceramic material. Plastics, you can make it super soft, like a plastic bag, very, very thin, transparent. You can make it really, really hard, like when they use it for, like the telephone that I showed you. It looks, it's shiny and it's hard. It's sometimes difficult to tell if you're dealing, by just looking at something, if you paint it silver, you can't tell if it's a metal or a plastic, right? So plastic has such a wide range of properties that we can control very easily through controlling the chain length of the polymer, the number of cross links, the kind of side groups that you add. All of those things give us a lot of control. So even though I know that in our society, using plastics, especially throwing away plastic, is really, really bad for our environment. But the invention of plastics has really changed our way of life, right? The things that we use, so many of the things are plastic, and you can't imagine your computer or your phone without plastic parts, right? How heavy would your computer or laptop be if it didn't have any plastic parts? Not just because of the weight, but because of the thermal insulation, right? If everything was made out of metal, you might have to shield it somehow, right? So that it doesn't conduct electricity. And the shielding will add additional size and weight to your laptop or phone. Other parts of it, you might have to use wood or glass or ceramic materials. But if you use glass or ceramic materials, just like your screen, it's very easy to break, right? So imagine your life if you didn't have plastic materials, like the clothes you wear, the umbrellas you use, right? What would they be made out of? Your raincoats, what would they be made out of? And so we have so much control, and nylon is one of the ones that was made, and it was first made in 1935, so a long time ago. And one of the most popular applications of nylon was for pantyhose or stocking. I don't know what you call it in Chinese, but do you know stocking and pantyhose? You know what those are? Things that you wear on your legs a lot of times. Anyway, so it was not socially acceptable back in 1935 for women to go outside with bare legs. You have to wear, and it also was not socially acceptable to wear pants. So you have to wear skirts, but then you can't have bare legs. So you have to cover up your legs, usually with stocking, okay? Something over your legs. And nylon became the replacement for materials for stockings. Can you think of what they used to wear for stockings before they had nylon? What would people wear on their legs instead? Cotton, of course, right? Could be cotton. Silk, right? Or wool. Okay, so silk, cotton, or wool, those are the most common materials that people use for stockings or pantyhose. And this is cotton that doesn't have any polymer additives, right? It's not, it doesn't have any stretchy, like spandex kind of feel to it. It's just cotton, like your t-shirt. And so it would be thick, and right, they can't make it that thin. Be fairly thick. Most people couldn't afford silk, to wear silk stockings every day. So most of the time it was wool and cotton. And it also doesn't stretch that well, so it would kind of sag, right? After you wear it for a little while, it would sag around your ankle. And they always wore those little clips to clip the stockings up because it didn't stay on. You have to hold it up. And so when they just created nylon, it was amazing for women. I mean, it became like the most popular thing, that it's thin, it's breathable, it doesn't get so hot in the summer to wear this, and it stayed up. It didn't sag around your ankles, it looked much better. And so nylon was really, really, really popular. When stores would sell nylon pantyhose or stocking, it would sell out right away. There are these pictures from the 1930s and 40s of people fighting in the stores. Whenever there was a nylon stocking sale, people would go and like try to grab what they can and push each other over. So it's hard to imagine anyone doing that for stockings nowadays, but it was, that was what happened. But then it's also used for parachutes and waterproofing materials. Okay, so before nylon, the military actually would use silk as a parachute material. Obviously, nylon worked much, much better. So when World War II came, different countries actually asked their citizens to stop using nylon for other things because they needed so much nylon for the military. And so that was one of those sacrifices that people made, was to go back to wearing cotton wool stockings instead of having nylon. So if we were to look at the mechanical properties of plastics, stress versus strain, what do you think the stress-strain diagram of a ceramic would look like? ceramics are very, very strong. Strength is, or stiffness, and very, very stiff. Stiffness is represented by the Young's modulus, right? The slope of the linear part. Okay, so very, very high stiffness. So it means that the Young's modulus is very high. The line is very straight up and down, right? Okay, very, very little. Imagine I drew a straight line. Okay, I'll use a different color. Okay, this is the ceramic material. Would it have any parts here? No, because it would not stretch before it breaks, right? It would just break. Stress strain diagram of a ceramic, very easy. It just has the elastic portion, no plastic portion. No permanent deformation. Metal, we had drawn before and will look something like this. It's strong, but not quite as stiff as a ceramic. Okay, something like that. It will have an elastic deformation area and a plastic deformation area. What do you think a plastic might look like? Would it have an elastic region, or would it be completely plastic, you think? So would a plastic material be able to have temporary deformation? Would you be able to stretch it and it'll return to its original length? Or bend it and it'll go back? A plastic material. You all have plastics on you, right? Are you able to bend just a little bit and have it go back to its original shape? Yes, right? Because when you're using your pen, you're bending it just a little bit, but your pens don't end up being weirdly shaped from you using it, right? It goes back to. So yes, there is elastic portion to a polymer because you're still able to stretch the bonds without breaking any bonds yet, and they're able to return. So you will have a lot less stiff than a metal, but you will still have an elastic portion where you can bend it and it'll go back to its original shape.
Professor, can I ask, what kind of material does the red limestone?
And then after you stretch the bonds, you'll start to break some of the secondary bonds. So it's very easy to break, right? It doesn't require much, because you could stretch those depending on the polymer that you made. You could stretch it out quite far. At the very end, you'll actually start to go up because now you're lining up your chains. You're lining up your chains, and eventually you will be breaking covalent bonds. So the amount of force you'll need at the very end actually goes up. I'll call it polymer to avoid confusion with the plastic region. But of course, you can also make plastics that are stiff. So if you made a plastic that's stiff, it might look something like this with a very little, right? If you have lots and lots of cross links, you can make a polymer that is difficult to break with a very little plastic deformation. And you can make something in between. Okay? So those are all different kinds of plastics that you can make. So the last thing I'll talk about in terms of plastics is there are two different kinds, the thermosetting and thermoplastic. Thermosetting polymer does not melt. So thermosetting polymers, you can heat it up, it's not going to melt, and actually start to degrade. It can start to fall apart, it can start to burn, but it's not going to become a liquid. Thermoplastic materials will soften as the temperature goes up and will eventually melt, so we'll have a melting temperature. Thermoplastic materials do not have high levels of cross-linking. So when you heat it up, the secondary bonds will break and the chains will be able to move freely. So they start to soften, becomes a liquid. Thermoplastics are easy to recycle because you could just melt the plastic down again, make a new thing, right? Thermosetting materials are highly cross-linked, and that's why they will fall apart at high temperatures, but they will not melt. And so it's not easy to recycle a thermal setting material. Which one do you think is stronger? A thermal setting material or a thermoplastic material will have a higher strength? Thermal setting, because of its cross-linking. So cross-linking is really good if you want a strong material, but if you want that material to be recyclable, it's not good. So those are two basic types of plastics. Could either be thermal setting or thermoplastic. And both have its pluses and minuses. So I think I'll end today, and then we'll finish off our class next Thursday with electrical properties of materials. And that will be my last lecture. It will be next Thursday.